in their own voices. Episode 1. Max Planck. I never planned to fracture physics. At 42, already grey about the temples and respected in the conservative circles of the Prussian Academy, I believed the universe was a grand clock. Its brass gears, thermodynamics, Maxwell's light, and the mechanical worldview of Newton clicked with solemn regularity. Even the soot-black cavity resonators I spent my evenings polishing in Berlin's half-frozen winters were meant to confirm that certainty, not shatter it. Picture those resonators, empty metal boxes painted as dark as coal, each no bigger than a child's lunch tin, punctured by the narrowest of slits. We heated them and watched the glow that leaked out, hoping the spectrum would follow the neat curve Lord Rayleigh and Sir James Jeans had predicted. Most nights it did, until December 1900. Just after St. Nicholas Day, Heinrich Rubens, bespectacled and usually unflappable, burst into my office with fresh data. I still see the snowflakes on his shoulders. "Planck," he whispered, sliding the damp sheets across my desk. "The longer wavelengths are misbehaving. The classical formula rises to infinity. But look!" He tapped a crimson cluster of points safely hugging the axis. "The real numbers stay finite. Something is deeply wrong." My heart thudded. I tried to laugh it off. A miscalibration, perhaps? Dust in the slit? But Rubens's hands trembled, and his instruments were beyond reproach. I dismissed the staff and let the laboratory fall silent. Outside, the Tiergarten lay under a brittle moon. Inside, I paced between the resonators as lantern light flickered, arguing with ghosts. Boltzmann's statistical demons, Kirchhoff's radiant walls, the shades of Clausius and Helmholtz. Could energy itself be granular, exchanged in packets, tiny, indivisible licks of flame? It felt heretical. Continuity was our religion. Heat flowed like water, not gravel. At 5 in the morning, ink frozen in its well, I scrawled the scandalous line: "Assume the microscopic oscillators may possess only energies that are integer multiples of a constant times their frequency." I labeled the constant h, merely a bookkeeping trick, I told myself, to mop up inconvenient units. Yet I sensed that once the door opened, no bolt would close it again. 1 week later, 14th December 1900, I faced the German Physical Society. My voice shook as I greeted them, "Meine Herren." I laid out the purely formal assumption, then unfurled a parchment with the newly calculated curve. The match to Rubens's data was perfect. Silence, heavy and electric, filled the lecture hall. Some leaned forward, others looked away. That evening, back in the lab, I touched the walls of a resonator, half expecting a spark. I did not foresee lasers, semiconductors, or cosmological backgrounds. I barely believed the quanta were real, yet deep inside I felt physics inhale, paused on a comma, before speaking a second sentence that would sound nothing like the first. Postlude. News travelled quickly. Young Albert Einstein wrote me a polite letter of thanks, then ran farther with the idea than I dared. Ludwig Boltzmann, tormented by doubts of his own, had already taken his life. I sometimes wonder if the discrete grain of energy that saved black-body radiation might have saved Ludwig too, had he lived to see its triumph. Still, in quiet moments, I recall the cold boards under my feet, the hush broken only by the hiss of gas lamps, and the single unimaginable leap from a continuous world to one built of quanta clicking like pearls on an abacus. That sound, if sound it makes, has echoed through every laboratory ever since. Episode 2. Albert Einstein. A dry, clattering wind swept along the Aar and rattled the shutters of the Bern Patent Office on 17 March 1905. Inside, the air smelled of ink, coal dust, and the stale crusts of last night's bread. I was 26, underpaid, and employed to judge improvements to egg slicers and telegraph relays. Yet Planck's miraculous constant, H, kept buzzing in my ears like a stubborn mosquito. "Why should only the walls of a furnace trade energy in chunks?" I muttered, leaning back in my wooden chair and staring at the ceiling. "Let light itself be particulate, little bullets, each carrying the same grain of energy Planck discovered. Across the scarred desk sat no colleague, only a leaning tower of patent claims and an iron stove that groaned in response. I imagined the stove nodding as I argued with the void. I pictured Philippe Lenard's experiment in my mind as if it were happening on the blotter. Ultraviolet beams striking a sheet of zinc, electrons hopping off the metal instantly. Classical wave theory predicted a slow simmer. Electrons should need time to collect enough energy. Leonard instead saw them explode free the moment the light touched the surface, provided the color was blue enough. No amount of red light, however intense, could budge them. Planck's grain offered a clean answer. Each quantum, each photon, as I would later call it, carried energy equal to Planck's constant times its frequency. If that grain exceeded the metal's binding cost, the electron broke free, all in one go. Simple, decisive, and scandalous. Over the next 48 hours, I filled 20 pages, writing in German so crisp it startled even me. I titled the work, A Heuristic Point of View Concerning the Production and Transformation of Light. It was a polite title for dynamite. I sealed the envelope to Annalenda Physik, kissed Mileva on the forehead, and said, "Today we send a small stone rolling down a very high mountain." Months crept by. I examined another 100 patent filings, some brilliant, most absurd. Then one morning a page proof arrived with Planck himself listed as the referee. He allowed publication, but appended a cautious note. The author's conclusion seems to contradict the wave theory of light. Further investigation is required. That was his diplomatic way of saying he found the photon idea hard to swallow. I understood. I too felt queasy, like a man proposing that water flows uphill. In the autumn, Leonard confirmed my formula experimentally. He telegraphed excitedly. Einstein's relation verified to high accuracy. Photo effect yields Planck's constant newspapers barely noticed. The academic world mostly shrugged. Otto Wien sniffed at a conference. Waves cannot come in pieces. I replied, zinc insists they do. By 1909, I realized photons must also carry momentum. They should buffet microscopic mirrors ever so faintly. I predicted a measurable jitter, tiny but not zero. The idea of radiation pressure fluctuations drew raised eyebrows. Someone scrawled in their program, Einstein slides toward metaphysics. I carried on. Mileva and I pushed our pram along the Aare, snow crunching underfoot. I would stop, toss a pebble, and watch the ripples. Each circle on the water reminded me that a single event could have both a particle's pinpoint origin and a wave's expanding reach. A paradox? Maybe. Or maybe reality was inviting us to duel in two languages at once. 15 years later, the Nobel Committee finally phoned, but they did not cite relativity. Too controversial, they said. They honored the 1905 photon paper. I laughed into the receiver. So you award the prize to my naughty child, the one most physicists still refuse to recognize. Yet I was grateful. Revolutions are strange. They need both radicals and reluctant midwives, and Max Planck had already performed the christening. When I left the patent office for Zurich, I packed a single cardboard box, some patent models, a violin, and a ream of blank paper. The mountain down which that first pebble rolled was still there. The rumble of falling rocks would soon ricochet around the globe. Episode 3. Niels Bohr. In the damp spring of 1912, Manchester smelled of coal smoke, yeast, and ambition. I, a lanky Dane of 27, had come to study under Ernest Rutherford, the man who had just torn the atom open and found a sun-hot nucleus inside. He greeted me with a handshake that nearly crushed my fingers and a booming laugh that shook dust from the rafters. Yet almost as soon as I saw his atomic sketch, electrons circling a positive center like gnats around a campfire, I felt uneasy. "Professor," I blurted over tea, "according to classical electrodynamics, those electrons should radiate away their energy and dive into the nucleus within moments. Where, then, is the matter of England?" Rutherford slapped his knee and roared, "That, my young friend, is your puzzle now." I lodged in a frigid attic off Oxford Road. The walls were thin. The British rain scratched at the slate roof like a pen scratching paper. Nights I paced under a single gas lamp, rolling Planck's constant between my fingers like a worry bead. What if the electron could occupy only certain allowed orbits, each with a fixed portion of angular momentum? No sliding in between, no half measures. Radiation would cease because no intermediate states existed. To test the idea, I drew concentric circles on the peeling wallpaper, measuring each with a compass borrowed from the workshop. Then I calculated the energy difference between two rings and divided by Planck's constant. The result whispered a frequency, exactly the color of one of Balmer's mysterious hydrogen lines. My heart thumped so loudly I feared the landlady would complain. At dawn, I barged into Rutherford's office. "Quantist orbits," I declared, waving a crumpled sheet. "Electrons may leap from one circle to another, emitting or absorbing a photon whose energy equals the difference between the two." Rutherford stared, jaw slack, then slapped my back so hard I staggered. "Publish, Bohr, before breakfast gets cold." The next year, a trilogy of papers appeared in the Philosophical magazine. Oliver Lodge, ever skeptical, wrote in a review, "The author's postulates are bold to the point of rashness." But spectroscopists were ecstatic. My scheme predicted every known line of hydrogen and many unknown lines besides. Sommerfeld soon extended my circular orbits into graceful ellipses, explaining fine details. I felt like a shipwright, watching others attach new masts and sails to a vessel I had barely christened. Back in Copenhagen, I built something rarer than any equation, an institute bound by conversation. Young geniuses, Kramers, Pauli, Heisenberg, drifted in like migratory birds. We drank Margrethes coffee and argued until dawn. On good nights, we solved puzzles. On bad nights, we invented better questions. One evening in 1922, Werner Heisenberg protested, voice hoarse from debate. "Your quantum jumps happen without cause, Herr Professor." "A physics without trajectories is sacrilege," I answered. "Perhaps causation dwells not inside the electron, but inside the question we dare to ask." He frowned, then scribbled something in his notebook that would later blossom into uncertainty. 5 years later, at the Fifth Solvay conference, Albert Einstein cornered me beside a blackboard. "God does not play dice with the universe," he declared, eyes smoldering. My pulse quickened. I replied softly, "Einstein, stop telling God what to do." Laughter rippled, yet the room knew a fault line had opened. That night, I wandered Brussels streets slick with rain. Sodium street lamps glittered like individual quanta of light, distinct, irreducible. I realized our quarrel was not about dice or destiny. It was about the strange marriage between observer and observed, question and answer. I whispered the Danish word complementarität, tasting its weight. The quantum revolution had become a mirror. In it, we saw not only electrons, but ourselves. Episode 4? Louis de Broglie. Paris in 1923 was a wounded city, mending itself with jazz and absinthe after the Great War. My elder brother Maurice tinkered with naval communications. I, Louis, the dreamy, stammering younger sibling, haunted the reading rooms of the Sorbonne. I was supposed to study history, the safe pursuit of our aristocratic line, but Einstein's particles of light refused to leave me alone. If waves can masquerade as particles, I mused one grey afternoon while walking along the Seine, perhaps particles carry hidden waves of their own. I watched ripples around a floating leaf and felt a chill. Could every electron be followed by a silent melody, a guiding undulation invisible to our eyes, only because its wavelength was unimaginably small? That night, in the library's tall shadows, I scribbled on a scrap of paper, "Energy equals Planck's constant times frequency. Energy equals mass times the square of the speed of light. Therefore, momentum must relate to wavelength in a perfectly symmetrical way." I tucked the note inside Principia Mathematica and almost forgot it. But the idea returned, insistent. I commandeered Morris's basement lab, firing cathode ray electrons at a fluorescent screen. Each green speck appeared where anticipated, yet I stared past the spots toward an unseen wavefront guiding them. Morris, annoyed by my reverie, said, "They travel as corpuscles." I replied, "Or as waves whose crests crash exactly where the dots appear." He challenged me to prove it. Unsure, I mailed a slender manuscript, barely 120 lines, to Albert Einstein in Berlin. Weeks later, a letter arrived. "Cher Prince," he wrote in meticulous German French, "your intuition is profoundly true." I read the sentence 10 times. Encouraged, I turned my notes into a doctoral thesis. The committee hesitated. Word spread that I was dabbling in mysticism. Paul Langevin intervened. Let him defend. Paris must not silence a new Copernicus. During the viva, I spoke softly, hands trembling. "Messieurs, every moving particle carries a wave, its length inversely proportional to its momentum. We do not see it because it is too fine, like the grooves on a perfectly cut gem." They passed me, some out of conviction, some out of curiosity. Real vindication arrived from far across the Atlantic. In 1927, Clinton Davison and Lester Germer observed electrons scattering from a nickel crystal, forming rings no particle should form, but every wave must. The same year, George Thomson, son of the man who discovered the electron, produced similar patterns in Scotland. Suddenly, my phantom undulation stood revealed, bright as day. At the 5th Solvay that autumn, Erwin Schrödinger seized my hands. "Your matter waves inspired an equation that may describe everything." He sketched symbols on a dinner menu, but I hardly needed the mathematics. I felt the music already. Later in life, I wandered into pilot wave theories and other controversies, yet the core revelation remained unshaken. Every shard of matter hums a note so high we call it silence. Those notes weave the cosmic fugue we call reality. Episode 5. Erwin Schrödinger. I fled Zurich in December 1925, lungs clogged by influenza and mind buzzing from Werner Heisenberg's latest paper, rows and columns of numbers, dazzling but pictureless. My lover Anne-Marie pressed a wool scarf to my chest as the train creaked toward the alpine resort of Arosa. "Go," she said. "Let fresh snow cure your fever and your physics." The Kurhaus sat high above the pines, smelling of wood smoke and camphor. Outside, winter sunlight glittered on untouched drifts. I skied alone, the hiss of powder in my ears, pondering Louis de Broglie's waves. On the third day, as I paused on a ridge with breath crystallizing, a thought cut in like a sudden gust. The electron is not a planet. It is a standing wave wrapping around the nucleus the way a guitar string wraps around itself in a closed loop. I raced to my rented room, fingers numb from cold. There, on hotel stationery emblazoned with edelweiss, I penned an equation that married energy, momentum, and de Broglie's wavelength into a single melodic statement. I solved for the hydrogen atom, expecting a tangle. Instead, the energy levels slid neatly into place, each predicted color matching Balmer's series with musical precision. I laughed, a deep, crackling laugh that startled the chambermaid. Returning to Zurich, I barged into Peter Daby's colloquium and filled the board with sine waves and boundary conditions. "Gentlemen," I declared, "quantum theory can be a wave theory in real space, as clear as ripples on a pond." Some applauded, others scowled. Heisenberg later wrote me, half in admiration, half in challenge. "Your waves live in a space of 6 dimensions. What kind of picture is that?" I published a quartet of papers nicknamed the January Revolution. Pauli wired, "Bullseye," yet soon pointed out that my theory still allowed visual models forbidden by the uncertainty principle. A duel of letters erupted. I, hungry for imagery, insisted electrons truly spread like mist. Heisenberg, wary, insisted the mist was merely a map of probabilities. Into this fray stepped Max Born. Over a rainy Göttingen evening, he proposed that the square of my wave function was not charge density, but chance density, the likelihood of finding an electron here, not its literal smudge. Part of me recoiled. Was reality to become a lottery? Yet the mathematics obeyed his reading with eerie fidelity. All these tensions came to a head in Brussels, October 1927. The conference hotel, dripping with chandeliers, hosted the sharpest minds in Europe. Einstein lobbed thought experiments like chess pieces across the board, a photon box here, a double slit there. Bohr parried with complementarity. Heisenberg sharpened uncertainty like a dagger. I argued for living waves, pounding the railing so hard the glasses rattled. By dawn, we were all exhausted, yet elated. We had not found the final answer. We had found the right questions. Standing on a balcony overlooking the misty city, I felt a quiet empathy for Schrödinger's cat, a hypothetical beast I would soon imprison in a paradox. The poor animal embodied my deepest worry. That microscopic ambiguity might balloon into macroscopic absurdity. But just then, the cathedral bells rang, and I realized life itself thrives on ambiguity. Love and grief, war and peace, particle and wave. Perhaps the cat would forgive me. Episode 6. Werner Heisenberg. Allergic hay fever drove me to the barren island of Helgoland in June 1925, but isolation did more for physics than medicine. The North Sea wind lashed the cliffs, and gulls screamed overhead like restless equations. I walked the jetty each night, lighthouse beams slicing the darkness into discrete flashes. Those flashes became my metaphor. Electrons do not follow smooth trails. They jump from brightness to brightness with black intervals we cannot observe. I brought only a stack of spectral lines for hydrogen and helium, data as stubborn as barnacles, and a vow borrowed from my mentor, Niels Bohr. Keep nothing that cannot be anchored to observation. So I erased orbits from the blackboard of my mind. Instead, I focused solely on the transition frequencies, the glow an atom emits when hopping between states. To keep track of these hops, I arranged numbers in square arrays, rows labeled by initial states, columns by final states. When I multiplied two arrays, something astonishing happened. The result depended on order. My innocent tables were matrices, though I did not know the name yet. Their non-commuting nature mirrored the stubborn fact that measuring position and then momentum gives a different answer than doing it the other way around. Returning to Göttingen, I burst into Max Born's office. Professor, I found a strange algebra that seems to capture atomic spectra exactly. Born peered over his glasses, then shouted, "These are matrices, Heisenberg. Hermann Grassmann would applaud." He, Pascual Jordan, and I set to formalizing the scheme, producing what critics soon dubbed matrix mechanics. Yet philosophy lagged behind algebra. I could calculate spectral lines with imperial precision, but what was an electron's path? One humid June evening in 1927, while wrestling the relation between measurement errors, I saw it. The more tightly you corral position, the wilder momentum grows, and vice versa. I framed the insight as an uncertainty principle, not a measurement flaw, but a property of nature. Presenting this in Leipzig, I sensed the audience recoil. Surely, one elder physicist objected, precision is limited only by apparatus. I answered, even the perfect microscope cannot sidestep this limit. The act of looking disturbs the fabric we look at. At the Solvay Council later that year, Einstein challenged me with his famous photon box. Weigh a box before and after a photon escapes to pin down both energy and time. Bohr invoked general relativity to defend me, showing the scale would itself blur under gravitational redshift. I realized then that alliances in physics are forged by necessity. Bohr and I, often sparring, now stood back to back against Einstein's artillery. Years passed, politics darkened Europe. I navigated perilous waters, directing Germany's uranium project under a regime I despised, yet could not openly defy. Critics later debated my motives. All I know is that when doubt gnawed, I remembered Helgoland. The salt wind, the lighthouse flashes, and the conviction that knowledge arrives in quanta, illuminated moments separated by darkness we must learn to respect. Episode 7. Max Born. Göttingen in the mid-1920s was a symphony of chalk dust and cello music. I often accompanied my friend Albert Einstein on piano, though he murdered the tempo. Still, the collaboration delighted us. During the day, I pursued a different harmony, the meaning of Schrödinger's newly minted wave functions. One raw November evening, as rain drummed the lecture hall skylight, I grappled with why Schrödinger's undulating curves reproduced atomic energies, yet appeared to smear the electron across all space. A flash of insight. The square of that curve behaved exactly like a density, an assignment of probability, not material. I tapped the board so hard the chalk snapped. "Gentlemen," I declared, "psi itself is not observable, but psi squared tells us the likelihood of finding the particle here or there." A hush followed, then cautious applause. I dashed off a note to Zeitschrift für Physik, framing quantum mechanics as fundamentally statistical. Wolfgang Pauli sent a postcard punning, "Born again." Schrödinger bristled, insisting electrons were real waves. I replied, "Better a statistical reality than a pictorial dream." The debate raged, yet experiments soon vindicated probability. Electron diffraction patterns brightened exactly where psi squared said they should. Life, however, cared little for mathematical triumphs. In 1933, Hitler seized power. The University of Göttingen, a jewel, was hammered into Nazi doctrine. My wife Hedwig and I, both Jewish, fled first to Cambridge, then to Bangalore. I traded German forests for monsoon rains and set about teaching Indian students the subtleties of lattice dynamics. They learned quickly. Suffering sharpens the mind. On sultry evenings, I would sit on the veranda, reading proofs for my book Principles of Optics, while geckos hunted moths under the lantern. I recalled my daughter Gritly once asking why stars twinkle. "Diffraction and atmospheric turbulence," I had explained. Now I saw a metaphor. Our knowledge of the cosmos twinkles because the medium between us and truth is restless, sometimes political, sometimes philosophical, always in motion. When the war ended, I joined the newly founded Max Planck Institute in Göttingen, ironically named after the man whose constant had launched our probabilistic century. I lectured that adopting probability did not cheapen reality. It humbled us, reminding us that nature's book is written in a code we can only partially decipher. Many nodded, some remained unconvinced. I told them humility, too, is a constant. One Planck never wrote down, but perhaps should have. Episode 8. Wolfgang Pauli. Sarcasm was my native tongue. I wielded it like a rapier, sometimes cutting friends along with folly. Yet in December 1924, even I hesitated before sending Niels Bohr my latest letter. It contained a principle stark and forbidding. No two electrons inside an atom may share the same four quantum labels: energy shell, orbital shape, orbital orientation, and an intrinsic two-valued property we would later call spin. The concept is ugly and stinks to heaven, I confessed, but experimental spectra left no alternative. In Hamburg, spectroscopists paraded puzzling multiplets before me. I pointed, barked, corrected. Landé's G factor, explained by my exclusion rule. "But where is the visualization?" they asked. "Attempting to visualize will only mislead you," I snapped. When Ralph Kronig suggested electrons literally whirl like tops to create spin, I withered him with a stare. Classical rotation would require surface speeds faster than light. Two Dutch students, Goudsmit and Uhlenbeck, dared publish the same idea months later. I scolded them too, though I had already softened, slightly, toward the picture. My temperament hid deeper wounds. In 1927, my mother committed suicide. I lurched through cafes, drinking too much, seeking solace in women and in physics. A disastrous marriage collapsed within months. Despair led me to Carl Jung's door in Zurich. The psychoanalyst listened as I described dreams of revolving diamonds and mirror symmetries. He dubbed my dark twin the Shadow. I retorted, only half joking, that even Dirac's sea contained holes. In 1930, beta decay mocked conservation of energy. Electrons emerged with a spectrum of energies, not discrete values. Bohr dared propose energy conservation might fail microscopically. I would not accept that. At a Tübingen masquerade ball, dressed as a pirate of all things, I penned an open letter to the radioactive ladies and gentlemen, proposing a tiny neutral particle to carry away the missing energy. I called it the neutron, later renamed neutrino to avoid confusion with Chadwick's heavy neutron discovered in 1932. I signed off, "Yours, the foolish inventor." Decades later, Cowan and Raines captured the elusive ghost, earning a Nobel I never received. I shrugged. Vindication was prize enough. My seminars acquired a reputation. When a young speaker's theory collapsed, I would declare it not even wrong, condemning it outside the realm of falsifiability. Yet beneath the scorn lay fierce love for precision. Better a sharp slap than a life of muddled thinking. After World War II, I joined the Institute for Advanced Study in Princeton, sharing cigars with Feynman, who delighted in my acerbity. Later, I returned to Zurich, lecturing on symmetry groups and the Pauli matrices, those modest 2x2 arrays that now anchor the quantum description of spin. I told students the exclusion principle is not a rule of scarcity, but of individuality. Each electron demands its unique identity, just as each human craves purpose. Some smiled, some looked puzzled, but they remembered. I died in 1958 in a hospital room numbered 137, the same number that mystically links the electron's charge, Planck's constant, and the speed of light. I chuckled at the coincidence, then closed my eyes, content that even the universe appreciated irony. Episode 9, Paul Dirac. Silence, to me, was a sacred instrument. As a boy in Bristol, I endured a father who insisted we speak only French at dinner, punishing mistakes with grim silence. Perhaps that upbringing tuned my mind to value words sparingly. When I reached Cambridge, I discovered equations could whisper truths more elegantly than any sentence. In 1927, I faced a problem both technical and aesthetic. Marry Schrödinger's wave mechanics with Einstein's special relativity. The hydrogen atom needed a description consistent with time and space mixing the way they do at near light speeds. My guiding star was beauty. An equation must be simple, symmetric, and inevitable, like a polished stone dropped into still water. After months of wrestling tensors and gamma matrices, objects few had heard of, I wrote a single line that hummed with internal balance. It predicted an electron whose spin emerged naturally rather than being bolted on by hand. I looked at the blackboard and whispered, "This must be right, because it is beautiful." But the equation also permitted negative energy solutions, states beneath the supposedly lowest rung. To avoid collapse, I imagined these states already filled, forming a vast sea. A vacancy, a hole, would behave like a particle identical to the electron, but with positive charge. 2 years later, Carl Anderson photographed a track curving the wrong way in a cloud chamber. The positron, exactly as demanded. Reporters called it a coincidence. I called it compulsory symmetry. Around the same time, I wrote The Quantum Theory of Emission and Absorption, introducing creation and annihilation operators, mathematical levers that pop particles into and out of existence. Jordan exclaimed that we had finally quantized the electromagnetic field itself. I merely nodded, already turning to the next problem. Conversation bored me unless it concerned physics. At conferences, I often sat apart, scribbling, while others argued. Once, after a long silence, Einstein asked, "What do you think, Dirac?" I replied, "That there are perhaps too many words already." He laughed. My marriage in 1937 to Margit, sister of the mathematician Eugene Wigner, drew me out. She teased me gently, coaxing anecdotes from my taciturn shell. World War II pulled me to MIT, designing radar components. Late nights I walked the Charles River, counting the reflections of lamps on the black water, comforted by their orderly repetition. After the war, I explored magnetic monopoles, hypothetical particles with isolated north or south poles, because their existence would explain why electric charge comes in discrete packets. No monopole has yet appeared, but the argument remains seductive. Retirement found me in Tallahassee, strolling under Spanish moss. Students still sought my counsel. I told them the last mystery, quantum gravity, would yield only to equations as spare and lovely as the others. When critics asked about interpretation, I shrugged. We must be content to understand the mathematics. Its meaning will follow. Even near the end, I carried a postcard, blank but for a single equation. Beauty, I believed, would finish the work when we are gone. Episode 10. John Bell. I was born to the clang of Belfast shipyards, where rivets ping like subatomic collisions. That background made me distrust fancy arguments, unsupported by nuts and bolts logic. So when I arrived at CERN in 1960, newly minted as both engineer and theoretical physicist, I carried a private irritation. The famous Einstein-Podolsky-Rosen paper still gnawed at my mind. Bohr's reply, in my view, had wrapped quantum mysteries in wordplay without touching the gears. On evenings after accelerator tests, I sat at a wooden desk in a cramped apartment above Lake Geneva, sketching diagrams of twin particles flying apart, spinning coins, forever correlated. Could a deeper theory, one with hidden variables, predetermine their fates while still respecting Einstein's demand for no faster-than-light influence? I translated that question into a simple requirement I called locality. Events here cannot instantly affect results there. From locality and a handful of statistical assumptions, I derived a set of limits, later called Bell's inequalities, on how strongly distant measurements could correlate. Then I checked quantum mechanics. The theory blew past my limits as if they were speed bumps on an empty motorway. I mailed the manuscript to a niche journal named Physics in 1964. Few noticed. 4 years later, John Clauser and Stuart Friedman built an apparatus with calcium atoms and polarizers, reporting a clear violation of my inequality. Still, skeptics cited loopholes, detector inefficiencies, timing flaws, communication possibilities. Then came Alain Aspect in 1982, closing most of those loopholes with a rapid switching experiment. When he phoned me at CERN, "John, we have it. 15 standard deviations." I simply said, "That is very nice," hung up, and stared out the window. I felt elation and a hint of sorrow. Local realism had been a comforting blanket. Now it lay in tatters. In public lectures, I emphasized, "My theorem does not say nature is non-local. It says any hidden variable theory consistent with experiments must be non-local. Quantum mechanics might still be a statistical veneer over something deeper, but that something cannot obey simple, classical separations of space and cause." Many listeners glazed over at the nuance, preferring headlines like "Quantum Spookiness Proven." So be it. Privately, I walked the Jura foothills, watching sheep drift across sunlit pastures. Their quiet order contrasted with the rebellious photons in Aspect's lab, yet both followed rules, one visible, one hidden. I took comfort in that symmetry. In 1990, doctors found lymphoma. I lectured at CERN anyway, thin and hatless. The moral of Bell's theorem, I told a packed auditorium, is that if we insist on a classical view of reality, we must accept influences outside our classical intuition, or we must abandon locality. Either way, the universe refuses to fit our prejudices. A young woman asked afterward, "Do you believe reality exists independent of observation?" I smiled. I believe the question is better than any answer I can give. That autumn, walking beside the Rhone in soft fog, I felt content. My inequality had become a compass. Others would sail farther, toward quantum cryptography, teleportation, perhaps quantum gravity. I would not see those lands, but I had helped chart the way.